It's not on. ये connect करो projector. The context is changed. Now we are transiting from a quantum computing to a quantum machine learning domain. Okay. Now what should be the requisite things to be learned here in the context of machine learning? Just try to remember. Okay. Now before that one, why we people are seeking the quantum machine learning based solutions for a real life problems? Okay. That should be the must. The things we should be at least understood. Okay. That why we people are emphasizing to go for a quantum machine learning, because if you see about the machine learning, there is nothing to learn. Understood or not? We know that what are that is the machine learning task, what are the machine learning applications to be, okay, where it may be applicable, but what's the significance of embedding or integrating the quantum computing aspects into the machine learning domain so that we can have some signified results? Okay, so what are the key aspects when we deal with the quantum computing? We are expecting what? High speed of computations? Yes or no? We are expecting what? Time reductions? Yes or no? Because as per our expectation, we have the time reduced complexity, means the reduced complexities of algorithms. Okay, and by default our expectation becomes what? That is to achieve some speed ups, because we have one of the dedicated machine that can allow us to have the intrinsic parallelization. We are not dependent upon any man-made parallelization in the artificial machine. Are yes or no? Are you getting my point? Whatever the parallelization we have, we people are intentionally incorporating these all into the classical machines. Okay, but the machine behavior is not like that. Understood? Other fact, if we see that the quantum computing is giving us the privilege to handle the high dimensional of data. Yes or no? Because the high dimensional data can be processed in just a step execution of time. So in the context of ये क्या हुआ भैया, चालू होगा नहीं होगा? What about the projector? I started not to waste time. But meanwhile, I was expecting you would be completing your setup. What happened? क्या हो? Where is the operator? टेक्नीशियन कहाँ है भैया, उसे बुलाओ जो भी है. It's on. Projecting. The lead is connected or not? USB connected. Yes. It's okay. Not in full color. Colors missing. It will come. It's okay. So now, what is our machine learning viewpoint here? That is, we are always dealing with the model. Okay, model that for certain predictions. Okay, for the purpose of classification, prediction, or the clustering, there may be a different types of machine learning tasks we use to handle, and for different applications, different perspectives we have. Okay, so if we look here, that is it working? अरे ये ऑन है कि नहीं है? No, it's okay. Now, so now what is our machine learning viewpoint here? That is, we need a scalable model, yes or no? We need the efficient model, that is the first thing. Other thing, if we look for, that is the feature extraction, that is the critical part, that is to deal with every of the data set, yes or no? So that feature extraction should also be done in an efficient way. Clear my point? Okay, that is why for the extraction, selection, these all purposes may be different, but we have to just come up with the refined data set to proceed or to train up our machine learning model. Clear or not? Such that the training time of the model can be at least reduced. Okay, that is the first aspect. Other is, that is to enhance the prediction accuracy. Right now the people have few of the people have already, I think, worked on the quantum machine learning tasks. So you may also be able to know that by applying a quantum machine learning solutions, after applying a quantum machine learning solutions, you people are not getting the expected results just because of the limited availability of the quantum resources. Okay, we have no such quantum resources available in a full strength. Okay, so anyways we have to compromise these things, and we are compromising. For every demonstration we have to just come up with the very small or build up model, because we have no such subscriptions. Okay, in order to just realize or just to demonstrate the things, we can go for the specific algorithmic model, that is, we can go for the model development accordingly with a very small scale purpose. Now the data visualization should be enhanced. The prediction accuracy is still what? It is at least expected as the classical model is generating. Okay, this is at least expected, but whether your quantum machine learning model is giving you the same accuracy or not, it is still a matter of research. Clear? Now another is the space would definitely increase if the dimensions of the data set related to gets increases. Okay, means if your data set is just dealing with the exponential number of dimensions, okay, so for processing such a data set, again that is the space would be more required. So for dealing with these all things, we have these quantum machine guarantees, yes or no? So in order to deal with them, that is efficient algorithm, scalable, so we have the high speed of computation machine, that is called quantum machine. Okay, and it is suitable for compute intensive and expensive jobs. But here whatever you are dealing with, the jobs may not be computationally hard. Okay, 90% of jobs are not hard, but the jobs requires the data to be processed in an exponential manner. Clear or not? So the expensive jobs are available to us, for which purpose we people are interested to apply what? The quantum machine learning solution. Okay, the time complexity reduction, exponential speed ups, these all are at all the expectation because of the high dimensional data representation is allowed. Clear? Through the quantum machine itself. So if we only check this is an intersected point, this is a target area, this is to work for, that is the quantum machine learning. Okay, now this is we have already discussed in the yesterday's slide. Now you look at the growth. You look at the growth. The quantum machine learning, the people have already derived so many solutions. The people have done lot of work for their quantum machine learning perspectives. But what's the progress of a quantum machine learning? Try to understand. The people are doing what? They are looking for the problem solutions. Okay, application specific solutions. Initially they think whether the classical machine learning solution exists or not. Yes or no? If the classical machine learning methods are available, so few of the researchers are working in order to transform such a same model into the quantum model. Getting my point? Otherwise, some quantum specific models can also be assigned, because the quantum specific model I am letting you know, it means what? Because the information processing system would be completely different. You know now. Yes or no? We are not dealing with 0, 1, we are dealing with cat 0, cat 1. Okay. So the thing is that whatever the like classifiers, okay, whatever the classifier we have in a classical machine learning perspective, the same classifiers would be there in a quantum. But additionally, we can have other classifiers which are dedicated for the quantum data processing. Yes or no? So this happens basically if we deal with the quantum machine learning solutions. Okay. But if we look for this solution, so this is categorized into the fully quantum machine learning and hybrid quantum machine learning. Okay. Fully and hybrid means what? This is relevance in that one. I already told you what all are targets. This is CQ and QQ. This is in relevance to SIMD, MIMD. Yes or no? So this is our current target. Classical data, encode it into a quantum compatible form, apply to the quantum machine learning model. Clear or not? Now, here, this is my ultimate target. This is called as quantum data to be processed onto the quantum algorithm that should run, means the implemented version should run onto the quantum machine itself. So, in relevance to that one, the research paper have already been published. Okay, like this is showing fully quantum machine learning, means it is based on QQ. And if you see, still these are the current instances. We are in a current scenario. The people have not explored because we have no resources what to explore. Yes or no? Even if we talk about in 2015, 16 or beyond that or before that, there were no resources available to just realize your experiments in quantum. So the things were complex that time. Similarly, the things are complex here in the context of quantum machine learning. Understood or not? So, but the people have explored hybrid quantum machine learning model. What does it mean? Hybrid means it's a combination of a quantum classical. Yesterday I told you, you do not assume that classical machines are lost, okay, or the quantum machines are the replacement to the classical machines. These are not such a scenario, okay. What would happen? The good mix of both the machines will be collectively taken in order to solve the realistic problems. Clear my point? So because of that one, this hybridness, it is to be called as hybrid quantum classical models. What to call? Hybrid quantum classical models. That is machine learning model, means okay, machine learning model algorithm is training over some data sets. Clear or not? So now, so the hybrid model the people have processed. So for they have categorized like in the optimization problems, okay. This is the specific problems, okay. Like quantum machine learning, sir, is there or not? Who was working? Oh, it's okay, let it be. Now the quantum kernels are there, like support vector machines, that is kernel transformations are required, where the data is not linearly separable in a lower dimension space. Okay, so we want to transform that data into the higher dimensional space and to apply some classifier for the linear transformations. Yes or no? So we used to do like that one. So the quantum kernels, neural networks, even the people have done so many things. And this is a specific thing, what it is written, but it is not categorized. It is parameterized quantum circuit. You may call it as variational quantum circuit also. Sometimes interchangeably the terms the people uses. Okay. So sometimes you may call it a variational circuit or the parameterized circuit. But what kind of circuits they are? Basically, whatever the data you have, they used to encode such a data in the form of some rotational circuits. Clear or not? So in such a rotational circuit, they used to call it as a variational circuit, because it is based on the data set what we are processing, and it equivalently they prepare the quantum machine learning solutions. Okay, but how it would be working, I will let you know in the later slides. Okay, if you see here, this is the processing steps. These are the processing steps. This is classical data to be processed using machine learning algorithm and go for the classical data prediction. Okay, but here at the right side, what are the two hurdles? Okay, the first one is you cannot proceed with the classical data. You will have to transform your classical data into the quantum compatible format. Okay. So because of the quantum compatible format here, the quantum encoding is required. Okay, means the quantum encoding, not only a single type of encoding, 4 or 5 famous encoding mechanisms are there. Like if you talk about the basis encoding mechanism, like angle encoding mechanism, like amplitude encoding mechanism, quantum RAM encoding, Hamiltonian encoding, so many, okay. But few of them are famous for that, okay. Now the same quantum machine learning, equivalent to the machine learning, the quantum machine learning algorithm would be here to process the quantum encoded data. And you visualize the thing, everything, your data is on the quantum circuit, your algorithm is on the quantum circuit, and the circuit gets processed at the quantum machine. Understood or not? So that your circuit is already prepared in such a manner that your quantum data would be processed by the algorithmic part of the circuit. Understood? Now, another is, once you are done with the quantum machine learning algorithm, what to come up with? That is to realize the solutions in a classical form. So we have to measure. So once you perform the measurement, once you done with the measurement, means you are getting the classical output, and it is expected as per the classical data prediction. Yes or no? So now, in order to have this pipeline on the right hand side, okay, we have the programming solution available with us. Yes or no? And we have discussed in the yesterday's session itself that how the features are incorporated in a Qiskit and why this programming language is becoming as a most popular programming language to program a quantum computer. Clear or not? Okay, let's proceed. Now this is my ladder chart. This is I used to just represent. Okay, this is just a kind of a ladder. If you want to work with the quantum machine learning solutions, okay. Now how to proceed? Initially, you define your problem, application specific. You go for your problem, okay, and check whether the machine learning solution is feasible or not. Till date, for every application, a specific perspective, if you think machine learning is applicable in every area, because it's now a interdisciplinary research aspects. Clear or not? In every area, whether you talk about the mechanical engineering, civil engineering, whatever the engineering you have in your mind, you may apply directly. Clear or not? So first of all, you think that whatever the problem you have in your engineering discipline, okay, according to that one you check whether existing machine learning solutions are available or not. If such a solutions are available, then we have to proceed for what? The quantum based solution. But in order to proceed with the quantum based solution, we do not have the data in a quantum available or quantum compatible format. So we have to encode our data first. Yes or no? Because once you know the data, then only you can apply the algorithm. Without knowing the data detail, we cannot proceed. So how to go? Now check for the quantum feature mapping to a quantum state. Okay, there can be a different possibilities like digital amplitude or the Hamiltonian expansions of your that is data encoding mechanism. So you will do. Now after the data is available in a quantum processing format, now check the same machine learning solutions or whatever the solutions you are having in terms of regression, if you are applying, or if you are applying for a clustering mechanism, or if you are applying for a classification mechanism, n number of classifiers are available. Okay, check which classifier to apply, or like the madam has done on a particular data set. If you are applying a 4 or 5 different classifier and just checking about the accuracy from which classifier we are achieving the good accuracy. So this is the general task of the machine learning, we need not to discuss. Okay, so now if you have such a machine learning solution, now choose a quantum design strategy. This is the important task here, because without design strategy you cannot implement your quantum machine learning algorithm. Yes or no? And based on your algorithm only, that to process your quantum encoded data, your circuit would become a quantum model. Yes or no? Because our expectation in terms of the quantum model would be a quantum circuit. Again, clear my point, where the data is also there onto the circuit, algorithm is also there in the circuit, and it is processing all. Clear? Now the thing is, So the quantum design strategy can be an quantum oracle based, yes, like an amplitude amplification. Few of the design strategy I am letting you know. I have already told you, not only these two design strategies, there can be n number of design strategies which are still available in quantum. Understood or not? Okay. So like quantum Fourier transform based, quantum phase estimation, quantum walk, hybrid quantum classical algorithms, these all are the techniques through which you can process or you choose your design strategy. Okay. Now after that one you go for the circuit designs, because I told you every algorithm is equivalent to circuit and every circuit is equivalent to algorithm. But at the last, what will run on the machine? Circuit. So we need to just come up with the circuit. Okay. So design your circuit, but the circuit should be an optimized circuit. If you do not optimize your circuit, so at the back end, the transpilers will also work to optimize your circuit related task, because it is also realizing some constants to realize your quantum algorithms onto the dedicated backends. Yes or no? So now after that, execution strategy you have to choose, that how you are going to execute your algorithms. Okay, means how you are implementing, efficiently implementing or not, or the basic implementations you are letting us know, or whatever the things you have in your mind. And now the next is classical post processing, because as per the previous, in relevance to that one, once you made that, means you are going for classical prediction of the data. So now here classical post processing is required, that is the evaluation of a results for validating your model. Okay. Once you have validated the model, you check for the quantum performance. You define your evaluation metrics. Okay, like several evaluation metrics we already have, like accuracy, precision, recall, F1 score. These all you people may define and you may check by your own. Clear or not? That how much was the accuracy there at the classical model, how much is the accuracy we people are getting in a quantum model. You try to compare, but think for a self again. Think for a self. If the two computational models are different, yes or no? So is it worth to just compare the performance of these two models? You think by yourself first. The computational is, that is the computational processing belongs to both the models are really different. We do not have the same thing what we people are having in a classical, but we used to what? We used to compare, because this is the adoption of the technology. Once the technology emerges, yes or no? So the people used to initially compare with the previous technology, new technology, yes or no? Yes or no? So the quantum is emerging technology right now. So that is why the people used to say, okay, the classical model is giving this accuracy, but now the quantum model, but with the less accuracy, then what to do? So what does it mean? The quantum machine is not an efficient machine. No, absolutely wrong. Why? Because the machine is enough capable of performing and of getting the more accurate results as well as the more enhanced results. But the problem is what? We do not have till date enough powerful quantum machine. But anyways, whatever the people are contributing till date, their research contributions are acceptable at all. Understand or not? The things are happening like in a manner. This is the life cycle. What do you think upon a qubit? Qubit have life cycle or not? Like us, the qubit is having a life cycle, if you agree, yes or no? When it starts in a superposition and when we measure the qubit, the life cycle of qubit ends. If you assume, whether you can be able to assume or not, I am letting you know again, we people belong to a quantum particle. We people are the quantum particle if we just expand the theoretical concepts of the cosmos theory. You just think upon that a particular cosmos, building of multiverse, universe, solar system, planets, earth, yes or no, coming to country to state to city to this place, yes or no. If somebody going to watch us, means we are only the quantum particle, which are not visible at all. Understand or not? So that would be again the problem. Now look at here. So the problem, the quantum performance evaluation is required. So you define your data matrix, criteria for comparison, you check what kind of comparison the earlier research papers have already done, yes or no? And it is not mandatory that the people are doing a particular comparison, so we are also supposed to do the same comparison. If you have the proper justification to let the other people know, or to let the research community know that this is not a valid comparison to do, you also try to publish it. Clear my point? Now, to proceed with the correctness and the completeness proof, we have to validate the solutions. We have to just go with the completeness proof, okay, for all. So now this is just a ladder approach, that is to deal with the quantum machine learning task. So this is just a quantum machine learning and an intelligence portion, because not only the quantum machine learning is emerging now. It's a total integration of a quantum computing with a machine learning part. But machine learning being a subset of AI, yes or no? Everything is approaching towards a machine intelligence. I used to call one of the famous journal is there, if I am letting you know, that is quantum machine intelligence. If you know, the indexing of the journal is still Scopus. It is not indexed in the SCI publications, but the journal is good. The journal is good for publication, okay. But what the people have the vision, they already predicted that we people are gradually transforming from an artificial intelligence to a quantum intelligence. Yes or no? Getting my point? So this is happening here. So many, like I told you in the previous this chart that is here, so many hybrid models the people have already suggested. Now if you see here, the quantum support vector machines are available, least square algorithms are available for regression purpose, classification purpose, for clustering purpose. But at all what we need, that some design strategy or to deal with that problem, okay, that how the particular classical solution can be converted or transformed into a quantum based solutions, yes or no? So if you check here, like variational quantum classifiers are used in order for the same purpose, okay, like quantum kernels are used, HHL algorithm being used, okay, to solve the system of linear equations, okay. Like here in a regression, system of linear equations or based on the HHL algorithm that can be solved. Means linear regression is solvable through the that is a kernel mechanism or through that HHL problem, okay, or that is HHL solution. Now the quantum distance estimation algorithm would be required if you go for the clustering. You will have to just check whether the data points are particularly separated apart or not, yes or no? So for that one we have to check the distance between the data points. For that one the distance estimations are required. We have to check for the swapping test in order to check for whether the states are overlapping states or not. That is some quantum states, because the overlapping must always be there. So the quantum states are overlapping states or not, we have to check it anyways, clear or not? So now like these, like for neural network also we have a deep learning applications, optimizations like high dimensional data representation, means the overall feature map be available here at a parameterized quantum circuit, okay. So this is the perspective of the deep learning. Slowly if you see here the machine learning significance, every task like image classification, pattern recognition, that is, or these tasks can be enhanced by applying the machine learning solutions, understood or not? And so many other things are also there, like natural language processing the people are working on, approximate optimization algorithms the people, if you may connect, okay. Some other AI specific task can also be benefited using the Grover search algorithm, because Grover's as well as a phase estimation approaches, they both play a very significant role for the generation or for the development of any quantum machine learning as well as the machine intelligent solutions, understood or not? Okay, are you connected or feeling tired of why I'm just looking at some few faces, or are you had a complete lunch, I think? So it's a recommendation always, whenever you attend a long length classes, means do not have a full food, okay, that is food to your fill. Now look at here, this is now a target, that is quantum state preparation and a data encoding mechanism, okay, because our task is to what? We always deal with the classical data right now, because we are at the hybrid model, okay. hybrid quantum classical model. So we are always dealing with the classical data that is to be transformed into a quantum space. Okay. So now for that purpose, this is my classical data that is to be encoded. For encoding purpose, we have this process. Okay. After this encoding mechanism, you may process through the quantum machine learning solutions, means in the form of quantum algorithms what you have, followed by measurement, and to get your classical output. This is the same, the pipeline is still same with different visual representations, nothing else. Okay. Now look at here. So now the classical data points, whatever you are taking, this is the classical data. Data points I am talking about still. Okay. If a specific data point is available, then the data embedding or the encoding schemes may be applied in order to just look your data into the quantum space. Quantum space means what? Hilbert space. Everything is available at your Hilbert space. Okay. So now you look. So once you look at here, that is basis encoding, amplitude encoding, angle encoding, sample encoding, arbitrary, several type of encoding mechanisms are available to us. But few of them we will be discussing here. Not only I would discuss actually, but we are constrained with the time, so I would not help. Okay. So now these are some, this is available in one of the published paper. Okay. So this is what? Basis encoding. So how the basis encoding works, look at here. This is, you have the input array of the features, and with that input array of the features only you check for the classical data representation for a particular point. Okay. So for if a data is suppose encoded in a quantum state like 0, 1, 0, like we processed just now, na, that is a phase estimation, 0, 1, 0, suppose like my data is 0, 1, 0. Now for the same data I am having the corresponding quantum data representation, means the classical binary string have now been transformed into a quantum state. This is a quantum state, it is a cat operator if you can see. Yes or no? Now if you see for the amplitude encoding mechanism, so for amplitude encoding you try to understand whatever the data representation we have, we try to encode the data into the amplitude of the vector itself. Okay, but how it would be achievable? Yes, it is achievable because our amplitudes gets expanded over a block sphere. Okay, so first we have to normalize the data. So once you go for normalizing of the data, it is now assured that okay, the maximum length of your data would be, that is 1. So it should always be contained within the unit sphere. Okay, so once you are doing like that one, so you can be able to encode your data into the amplitude form. So your amplitude must be containing the data. Like, let me connect. Just before the session, we did what? The phase estimation. We were dealing with e raised to the power 2 pi I k, 2 raised to the power n of theta divided by 2 raised to the power. This was what? This was actually an amplitude encoding mechanism that is already associated to the state J. Yes or no? Are you getting or not? Connecting at least. Huh? Now listen. So that's it. Now another is angle embedding method. So whatever the data points we have, the same data points we will be what? Encoding in some rotational angle forms. Okay. And this is rotational angles. Rotational angles we have like Rx gate you apply, Ry gate you apply, Rz gate you apply. So based on the value of certain theta, okay, you may encode your classical data into a quantum state. Understood or not? Now the other encoding mechanisms are also there, but in perspective to this angle encoding mechanism, I'll let you know one of the dedicated feature which is provided by a Qiskit programming framework, that is called as ZZ feature map. Okay, so that ZZ feature map allows your data to represent your quantum encoded or quantum compatible format of processing. Okay, now here you look at the quantum data processing that is related to the basis encoding mechanism. Okay, for basis encoding mechanism, if you have the binary string like x1, x2 up to xn, okay, whatever, if suppose you are working for a 3-qubit system like 0, 1, 0, 0, 1, 0 is my binary string to be processed through the classical machine. Now in a quantum machine, On a quantum machine, what we are looking here as the same data to be represented in a quantum state format. Are yes or no? So this is the like if I have the data as 1 0, so this is a quantum encoded format of 1 0. Now look at here, what the amplitude encoding is doing. This is just a representation of a classical data into the amplitude of the quantum state itself. Yes or no? If you look at here, if associated to each quantum state I, there is what? Xi, where Xi must be what? The amplitudes. Yes or no? So what we need to do before processing onto the data processing part, we need to normalize these all amplitudes. Okay. So what to do? That is, if this is suppose a classical data point, this is the classical data point. This should be a vector. So we should represent it in the vector form. Okay. So if the vector is available to you, so that vector is having these 2 points like x 3, 5. So if it is a vector, then in order to normalize that vector, we have to take this mod. Okay. Now this is what? This is the square root of squares of data points. Understood or not? So once you go for with, you will get this value of 5. Now your another amplitude, means your updated amplitude, what you encode in a quantum format, would be what? This is 3 by 5, 4 by 5. Getting my point? And still this 3 by 5 and 4 by 5 are the probability amplitudes. And how do we ensure? Apply the modulus square. 3 by 5, 9 by 25, and 4 by 5. If you take the sum, 1. Normalization condition at last satisfied. Understood or not? So this is how the entire amplitude encoding mechanism work. Okay. Your data remains encoded within the amplitude of the quantum state itself. Clear? Now the another is, that is angle encoding mechanism. And here in angle encoding mechanism, whatever the quantum states you have, okay, or the classical data points you have, for each classical data points you apply certain rotational angle operations, okay, based on some specific theta values. For every data point you can have a different theta value. Clear my point or not? Okay. So this is a kind of angle encoding mechanism like this. In this angle encoding, like this is 0. Okay. I am assuming that, okay, all qubits are initialized to 0. Now on the initialized 0 qubit we are applying a Rx gate. Okay. Means the rotational gates we are applying based on X, that is poly X. Clear or not? And we know that the corresponding matrix cos theta, minus sin theta, and I sin theta. Yes or no? So there is a rotational matrix operator when you supply what? The quantum state. So that quantum state would be transformed to the another state. And the quantum system knows. Yes or no? The quantum system knows about the fact that how did it transform from the classical data into the quantum format. Yes or no? So now here this Rx is applied like this, Ry is applied. Yes. But if you observe, look at here. This is Rz. Yeah? I did not apply through what? Direct, like this Ry and Rz. Rx. Why? I appended Hadamard here. I would have been appended Hadamard here also. But I did not like. Why? Reason is simple. Z performs no operation on 0. Yes or no? There is no impact of applying Z gate on 0. There should be at least one quantum state available within the system. So we take the expansion of the entire system either to be 0 or to be 1, so that whenever your quantum system becomes, quantum state remains present in a 1 state, the Z operation can be supplied. Clear my point? Now, this is just a simple thing, that is a basis, amplitude, angle and ZZ map. This is for the future perspective I have written down here. Now, these all encoding mechanisms requires the qubits. Like basis encoding require all n qubits. Angle encoding requires all n qubits. If you are dealing with n, means n qubit. But in amplitude encoding, only log of n qubits are required. Because only if you are dealing with n, means you will have to work for log of n values, because these are the associated amplitudes. What do we consider? If suppose you want to represent two quantum state, how many qubits you need? There are two quantum states I want to represent. You just listen my question first. I want to represent two quantum state. How many qubits I require? That's it. Yes or no? So the simpler. Why? Because I have the two data points like 0 and 1 and I want to encode that data point. So but the amplitudes would remain same na? Yes or? So that is why the log of n is the fruitful factor. Clear my point? Now look at here. So sorry, now look at here. So the complexity is easy, hard, moderate, like this. Okay, the things are now available, but the application specific data encoding task the people used to perform. Understood? Okay, that which type of encoding mechanism would be required in order to process for a certain application. Okay, so you will have to look at it. Now come on to the other fact, that is a quantum based feature mappings. Okay, using kernels. Now the feature map, that is to transform a new space, that is a data into the new space. When we used to transform, I just discussed before, because whenever we are looking at our data into a lower dimensional space and the data is not linearly separable, okay, and I want to classify the data, but if it is not possible to classify in a lower dimensional space, we used to transform. Okay, so once you go for transforming your linear, that is a data into the higher dimensions, so we need some kernel transformations, because at the last we should have the mapping relevance. Yes or no? How we are mapping our current point of the data to the other dimensional spaces. Yes or no? So such a transformations are already possible in a classical compatible formatting. Yes or no? So the similar concept the people have taken here, like this x belongs to a real number. Okay, now this is to be encoded in the other m dimensional space. So n is now encoded to m dimensional space. Now if the model is suppose a linear model, you are applying like a support vector machine onto the transformed space, then it would work. Yes or no? But if you apply on the same lower dimensional space, so your model will not work. Clear my point? So the thing is that because that classical solution was available, I told just before, okay, before, that is 15 minutes I think. Okay, if the classical things are available, then only you may at least think for the quantum version. Yes or no? So if the feature map construction was available in a classical manner, so the quantum feature mapping is also possible. Yes or no? So for the quantum machine learning task, we do the similar thing, used to encode our classical data in a quantum compatible formatting. We know that several encoding mechanisms are also there, but such a data should always be expanded over a Hilbert space. Yes or no? So once the data is expanded over our Hilbert space using a unitary operator, so this is the unitary operator. Okay, this unitary operator have to be supplied to a that is our data. Okay, so in order to transform that data into the other dimensional space, the context is changed. You try to understand. The first context in a classical perspective is what? Lower dimension to higher dimension. That is the first thing. Here, the perspective is different. We are dealing with what? Classical dimensions. Now from classical dimensions to quantum dimensions. Getting my point? And anyways, quantum dimensions always explore the exponential possibilities. For one qubit, how many quantum systems? That is how many quantum states? 2. And it remains in a 2 raised to the power 1 dimensional quantum system. Yes or no? For 2 qubits, 4 dimensional quantum system. N qubits, n dimensional quantum system. So if you have such an expansion of the quantum system, so by default you are moving from the lower dimensional space to a higher dimensional space. Like a kernel, like quantum kernels are also applicable, like in classical kernels. Okay, like from lower dimension to higher dimensions the people are moving. Okay, that the data point should be moved. So here that quantum kernel mapping is also possible at all. Clear? So now this is to be called as, what to call it as? That is the encoded classical data onto the Hilbert space through that unitary operator would be called as what? The quantum feature map. Okay, so this x state first, it would become what? Phi of x, and this is a ket operator I used again. So based on this ket operator, what we used to call, that is the encoded quantum state. This is the encoded quantum state first. Okay, Based on this encoded quantum state, we apply this unitary transformation, that is a quantum circuit, whose parameters are derived from the classical data vectors. Okay. So whatever the data vectors or data points we have, based on that one, this transformation can be applied. Okay. Now you look. So this state lives in a high dimensional Hilbert space. We are already discussed this thing. Okay. And yes, ma'am.
These are only we will call them as vector databases.
I am not getting.
Vector databases means these are only, no, sir.
Yes. Now, why we are using here the quantum feature mappings? Like the quantum computers can naturally explore the exponentially large Hilbert space. We discussed. Just now we discussed. Okay. Now the feature maps that encodes the classical data into the complex quantum state. And we know that how do we just go for that is encoding our data into the quantum state. I will demonstrate through the Qiskit program also, that how the quantum data gets encoded into a classical data gets encoded into a quantum compatible format. Okay. It allows high dimensional structures without explicit mapping and enables the kernel based learning through the inner product estimations. Okay. Now the quantum kernel, if we talk about, is still the same, the concept is same. The kernel is used to just check the similarity between the two quantum states. Okay. So the quantum states what we have, okay, we have to just check with the similarity, and for checking with the similarity we have to deal with the other things also. Not the directly quantum kernel mappings are possible. Okay, we have to deal with the other requisites or the other essentials related to the quantum machine learning that is to be understood at the primary level. Clear? So now, if you see that this is the kernel mapping from x to x prime, okay. So now, because this is not available, we are dealing with the quantum encoded data. So if you see like this, this is what? This is bracket. Can you be able to see? This is bracket, and what we used to call this phi of x, it is an encoded quantum state, yes or no? So now that encoded quantum state is being squared, means the modulus square is being applied here. Okay. So based on this one, this is used to measure the similarity between the two quantum states, based on which this is the inner squared product. This is the inner product. Bracket means inner product. Okay. So when you apply the inner product between the quantum state, means the encoded quantum state, so you will get the corresponding similarity between the quantum states. Like in a simple approach, you just think at the beginning level of your quantum course. I think I did not take that session, but you try to connect. If we have the two quantum states like 1, 1, okay, now I am checking 1 on 1 with inner product, what would be the solution? Answer should be inner product gives you what? That is 1 cross 1 information, that is scalar value, classical data. Okay. So 1, 1 means 1, 0, 0 means 0. It means what? Means your quantum system is expanded with 0 and you are looking for a 0 within the expanded system. It means like this. It used to called as like that these two states are similar states. They have some likeliness, yes or no? But this is very basic level of understanding that 0, 0 and 1, 1. If you apply the inner product, means the output should be 1. But what if you take 0, 1, 1, 0? It should be 0. Why? The reason is simple, because they are orthogonal to each other. They are not similar states. Yes or no? When you apply the inner product on 0, 1 or 1, 0, you will get the output as 0 always, because orthogonality. Okay, so due to the orthogonality condition, you can declare that these two quantum states are not the similar states. Okay, so similar concept is taken here. Okay, like here in a classical kernel method QSVM, you may use these quantum kernel methods. Like 1, the state, the 1 if you are getting as an output of this modulus square, it means what? The states are identical, these are similar. Like similar the 0, if you are getting the output of this inner product, means these are the quantum encoded data format. Yes or no? So these are the quantum encoded data format. If you take it to be 0, okay, So it means if you get it to be 0, means they are orthogonal. They are not the similar states. The data points are now different. Understood or not? Because you have encoded the data point in a quantum format. Clear my point? Now, so let's here like classical kernel which are still limited. This is the problem actually for the classical kernel, that is to deal with. That is, they were limited with the polynomial feature expansions. Okay. Here at the quantum kernel, we are already dealing with the higher dimensions, means the Hilbert space is already exploring the exponential amount of space. So already we are dealing with the exponentially large size of quantum space. So everything would be possible here. We are not limited now. Okay, we have expanded till we can expand. Oh, yes or no? Now, the thing is that the quantum kernel can represent the complex patterns efficiently by using the entanglement and interference patterns. Okay, so these patterns to be identified within the expansion of your data. Now, the feature map here in our context, the feature map to be called as the quantum circuit used to encode the input data. Okay, so whatever the input data you have encoded that input data into the quantum circuit format. Okay, and this is the way we used to represent that data. Now here comes the point, that is the ZZ feature map. This is what we discuss, these all different things, because the data encoding mechanism, like if we talk about the basis encoding, angle encoding and amplitude encoding, these have been over. Okay, but directly I am now shifting towards what? ZZ feature map. Okay, so this ZZ feature map is allowing, it is a parameterized quantum circuit here. Okay, and this parameterized quantum circuit is supported by the IBM Qiskit itself. Whatever the data you have, the data can be encoded directly using the ZZ feature map. Yes or no? But the ZZ feature map can be that is prepared based on certain restrictions. Okay, or based on certain rules. There is actually an algorithm through which the ZZ feature map gets created implicitly by the quantum framework. Okay. Now, how the ZZ feature map can be now implemented using a Qiskit? Suppose in a Qiskit for n inputs, already we need n number of qubits because it is an extension to the angle encoding mechanism. Okay. So now from x1 to xn there would be n number of qubits and we need to go for, this is the algorithm. This is the simple algorithm. If you look directly onto the circuit, you may just be able to just that is iterate these algorithmic steps. That is the first one. Apply Hadamard on each gate. Yes. Then apply on each qubit j a rotation gate. That is which gate? RZ. I told you in the previous slide. If you connect, why this z is already appended over x, over h, because we need one quantum state to remain present there. Okay, so the extension of this one of the rotational angle is now taken here in what to call it as, that is ZZ feature mapping. Okay, that is the purpose. So now after that one, a rotational angles are supplied based on these x1, x2, x3. These are some inputs, your input data. Okay, so based on your input data, you are applying this rotational angles. Okay, like RZ, you are applying. After that one, you will have to run for this step for 3 times. Like this is first, you apply the C0, means the A and C operation is same. That is to apply the C0. C0 between every pair of qubit wires. Okay, if there are 3, so 3 pairing will be done. Okay, like this is first, second, this is first, third, this is second, third. Clear? And in between that one, again an RZ feature map, RZ operation is applied based on the value that is taking from pi minus of xj, where j belongs to the first qubit wire and xk belongs to the second qubit wire. So based on this, that feature mapping is applying the transformation in order to obtain the quantum data. Getting my point? So now this is the complex feature mapping scheme, and that is why this is supported directly by your, that is a Qiskit feature, that is Qiskit language features. Okay, so you may directly use these as just only you will have to mention your data points. Okay, once you just mention your data points, you will be ready to just map or to encode your data points onto the quantum Hilbert space. Clear? Now, this is just a simple description about a quantum variational circuit. So should we move initially with the quantum variational circuit, or should we take the demo of angle encoding mechanisms? Just asking you all. What's the time like?
2:40.
We have time. No. We are scheduled up to 4 o'clock. Okay. So now what to do? Encoding mechanism, should I demonstrate? है ना? So few of the people, those who are feeling sleepy, na, so they can connect. Okay. Okay. Okay, look at here. These are, the fonts are available, visible. Now we know already that a quantum circuit, for what purpose we include, okay. Transpile, we include air simulator, histogram plotting, state vectors, you know. Now this is the ZZ feature map. This is for a specific purpose. Actually this program, this Qiskit code is containing all data encoding mechanism. And one of the dedicated cell I will be using to, that is to encode our data using the ZZ feature map. Okay. So just because of that one, we have just imported in the first cell. Okay. So ZZ feature map we have taken. NumPy for mathematical operations, and for visualization purpose we have taken that's matplotlib. Okay. So I think the importing of library is done already. So let's run it. Let it connect to the kernel. Connected. Okay. Now, so our, what to say, that is the library have been imported. Okay. Now after that one, basis encoding mechanism. So this is a defined, this operation, this method have been defined separately for the encoding mechanism. So this this basis encoding means what? Whatever the binary pattern we have, the same binary pattern to be encoded in a, that is in a cat vector format. Okay. So the same data to be passed. So the binary encoding if you see here, like this, let me here. Basis encoding is a method that would take what? Binary data. Look at here at the board, please. Now this is the binary data we used to pass. Okay, so we will be passing one binary string here. So once the string would come to this scope, okay, it initially check for the length of the binary data. Okay, the binary data length will be calculated, it would be assigned to n. Now based on the same n, the quantum circuit gets created with the same number of qubits and same number of classical bits. Okay, now for all I, that is and bit in a string that we should enumerate, because we are reversing our binary data. What we need about the binary data to be reversed? Suppose the data is 0, 1, 1. Means what? How do we interpret? 0, 1, 1 means 3 in a binary 3, but we used to enter like 0, 1, 1. Okay, so 0, 1, 1 should be encoded like in a similar manner. Okay, so that is why for LSB based processing it is to be written. So if in any of the enumerated string, if the bit is assigned to 1, so for that string we have to apply the NOT gate. So once you have applied the NOT gate, means your data has been encoded into the binary form. Otherwise there is no need to apply any gate. Clear or not? We have checked this in a classical demonstration of the, quantum demonstration of the classical gates. We set our inputs based on X gate or not to apply with the X gate. Clear? Now and after that we have to measure. Okay. So the data is ready in that context. So this is basically a definition of the function, but still we have to pass. Still that is the data have not been passed. Now to run our algorithm, simulator is ready now. This is the basis encoding demo. This would be a printable prompt message. This is the basis encoding, the method what we are using. This is the basis encoding. Okay, so here the basis encoding method is being called with the argument 011. Yes or no? So with that 011, now rest of the thing is related to transpiler, simulator, run, backend, counts, measure, etc. These all you people are known. Okay, we people have been discussing these all things redundantly since the yesterday. Yes or no? So now let it be with these all discussions, run it. Now you see what the data we have done, 011. Okay, so 011 means we are looking for what? 3. Okay, so because of Q0 is a LSB, Q0 is LSB and here Q2 is MSB, so it is written as 011. So this data is now available in a quantum compatible format. So whatever the input data which was available for the purpose of processing in a classical one, that is 011, so the same data is now been encoded in a quantum compatible format. Clear? Now let's move. This is let's plot the histogram known as no significance of just plotting it, but because it's for all time this data has been encoded. Okay, but there may be a possibility again to run the same circuit on the machine. Okay, so once you run the same circuit on the machine, so there can be a possibility of marginal errors. Now this is all about the amplitude encoding mechanism. So in amplitude encoding mechanism, what we need? An amplitude vector. First, okay, we need the vector like 3 and 5 we discussed in a slides. Yes or no? 3 and 5, 3, 4 I think, hai na? 3 and 4 we are passing as a data point, suppose. So 3 and 4 if we are passing like, so it should be normalized first. After normalization that would be like 3 by 5, 4 by 5, it would be becoming like that one. And it would be encoded within the amplitude format itself. So how the data would look like into here in a quantum version, just look at here. So first what to do? Amplitude encoding is a definition of the method. Okay, here this is the parameter to be passed, amplitude vector. Followed to that one a numpy instance we are using with the linear algebraic function in order to calculate the norm. Norm means would double. Okay, that is the norm or the magnitude of that vector. So we want to just calculate that norm of the vector here, and this is to be assigned in a variable called norm. Okay, so once this norm means the square valued, squared and a root value of that one. So once that would be just computed here, the normalized vector would be what? That is amplitude vector divided by its norm. That is like 3 by 5, 4 by 5 we used to write like this. Yes or no? We have already discussed this thing. 3 by 5, 4 by 5, this is the way. And next is the state vector to be now represented using based on the normalized vector. But this is still a definition of the function. Okay, if the method is defined here, the method is of none of use. Yes or no? Until unless the method is not called. Do you agree or not? Huh? What's our method? We all people belong to a faculty. We are all the faculty people. Okay, so our method is defined, teaching. But when we teach, if somebody calls, if there is no timetables, no schedule, no classes, no teaching, yes or no? So let it be. So now let's go for amplitude encoding demonstration. So it is amplitude and now the same data 3 and 4, that is for your visualization. That is like 3 by 4, 4 by that is 3 by 5, 4 by 5. Are we getting or not? Okay. So now the state data, the data is 3, 4, and we are passing this amplitude data to the amplitude encoding method. Okay. So once this amplitude data would be passed here, that would be working. Okay, and after that one their corresponding state vector would be available to us. Okay, now after that one the state vector to be printed in the form of state amplitudes and over the block sphere. So this is the block sphere I am using here to draw based on the state amplitude values. Okay, so whatever the state amplitude values we will be getting, like 3 by 5, 4 by 5, okay, these two values will be plotted here over the block sphere. So let's run this code. You check it. Okay, if you see, this is what? अरे यार ये कहाँ से आएगा? ये आगे पीछे हो जाता है. You see here. You see this thing. What's the state vector? This is the amplitude. This data is encoded. And if you see, this has now outer than this circle. Yes or no? Because of the data has been now encoded. It is not a normal qubit, this is moving around the circle. Okay, the data is encoded over the block sphere. It is assured that the unit length would be maintained anyways. Okay, so now if you see, what is the value here? 0.6 plus 0.j. So 0.6, 3 by 5. 3 by 5. What do we, sir? 3 by 5. 3 by 5 is 0.6. That's it. What about 4 by 5? 0.8. So the data is encoded. But it would not look like that. That what we assume, okay, our data is okay 0.6, like 0.8, but it is not looking like, because it's a complex vector. Yes or no? So the data would be different. The processing is completely different. We can't help it right now. So first we need to understand with the data. Data क्या है, तब तो data set process होगा. Yes or no? Clear? Now let it be with this. Now next come to angle encoding mechanism. Okay. So in an angle encoding mechanism, again an angle encoding method is defined with some feature vectors. So feature vector needs to be passed here. Okay, और इसको हटाओ यार, ये बार बार मुझे करने नहीं दिया. हाँ, the feature vector is passed. Now the length of the feature vector to be calculated. Okay, because this is angle encoding, na, the same number of qubits we require. Only in the amplitude encoding we require the log of n qubits. Yes. So now the quantum circuit is prepared based on the same n length. After that one, again that is to be enumerated for all the feature vectors. Apply what to apply on each qubit. What to apply on each qubit I? That is an angle. Clear or not? So angle we need to define here, that which angle we are passing. Okay. Now at the last, perform the measurement. It is a similar definition as per the basis encoding what we had. Now if you look at here, our time is left by 1 hour. Okay. ठीक है. Now looking at angle encoding mechanism. So now angle encoding, in an angle encoding, this is an angle data. Okay. So now data vector we have to pass. So this data vector is a numpy is an array that pi by 3, pi by 2, pi by 4. These are some rotational angles. Okay, we people are passing to the data itself. Okay, pi by 3, pi by 2, pi by 4, like this. And an angle encoding method is called with the angle data. So this is the angle data. Yes or no? So the angle data is being passed to the function. So once this feature vector would receive that data based on the values of the angle and I, it just encode. Clear? Now after that one, the transpile, simulator, etc., these all are known. Okay, nothing. Yes, we know. Okay, so let it run. It's done. This is how you will be able to see. Like we saw it in a Grover's implementation also. Yes, in a Grover's, whatever the data is there, you can be able to see, okay, unitary is there. Like, so if here, because a separate unitary is applied, like Rx, 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 or here what applied, Ry, Ry, Ry. But if you see, this is pi by 3, pi by 4, pi by 2. This, the data information we have applied. Yes or no? We supplied this data that we need our data to be represented in such an angle. Yes or no? So like after that one, and the same to be extended over a ZZ feature map, where we do not need to take care. Okay. Now, this is for your demonstration purpose of your data. Okay, look, that is the same angle encoding mechanism. This is the direct data plotting. Like if we have the classical data of 0.2 and 0.8. Okay. So if we have a classical data of that is x1, x2, like these two data points are there, like 0.2, 0.8. Now we are just calculating their theta values based on some encoding of the angles. Okay. Like using a numpy dot pi multiplied by x1. So whatever the x1 data point is there, that is to be multiplied with by and multiplied with what? 2. So that would be the another theta 1 value, theta 2 value, and that is to be passed. That is to be passed here in Rx gate. Okay. So once you pass these Rx gate with the values of index, these are the indexes. Okay. 0 and 1 qubit. So you will have some another encoding, that is the same encoding mechanism to be visualized like this. This is Rx. Now you see, this is 2 pi by 5, 8 pi by 5. This is as per what? Rx gate. Earlier in this one, which gate applied? Ry. So just remember that this Rx is now supplied with 2 pi by 5, 8 pi by 5. Let us just replace it with suppose y. Okay. Let me run it again. Now, this is again, the angles are same because the theta value you are passing is remaining same. But instead of Rx, it has been applied on Ry. Means it is based on poly Y matrix. Okay. That previous one was based on poly X matrix. Clear or not? Okay. So that remains possible always. So just simulate it. You check. This is your data. These are two data points. 0.2, 0.8. What we had. Yes, 0.2, 0.8, or it has been encoded in 2 pi by 5 or 8 pi by 5. So if you look at the representation of the data at the block sphere, so this is how your data is looking like as per Ry gate. Okay. So if you see, this is about Rx. Now you see, yes, Rx. Now you see, the data is changed. Okay. Now let's try for the magic. Okay. What's remaining now? Z. Now you let me know what would happen. Rz is applied. What should happen? Oh, both are at 0. No impact. Yes or no? Was okay. So because the data points are closer to 0. Clear? So if the data points are closer to 0 means Z have no impact on that data point. Okay, we are only looking for the closer values of 1. That is the problem. So now which rotational gate you are interested to apply, it would be up to you. It would be just based on your visualization, that what kind of data representation you are having in your mind. Clear my point? Okay, let's proceed. This is the ZZ feature map. Okay, so with the ZZ feature map, this is a definition, input vector to be passed, and representation actually used in order to show the entanglement between your data. Okay, so whether the entanglement we are providing between the data or not, means the data remains entangled or not. This is to just show the representation. Okay, so that is REPS. Now followed by that, a dimension we need to compute, because similarly the n number of qubits are required. Okay, so the length of the data to be computed first. So once you just compute that data based on that one, the ZZ feature map, this is the dedicated function, because we have already imported. Understood or not? We have imported the ZZ feature map. So from this ZZ feature map, we are assigning a feature with the number of dimensions what we have calculated, followed by what? That is, the representation is representation because it already been assigned as 1, We are just making them entangled, and followed by, we are just specifying whether that entanglement what we people are looking for is a non-linear or a linear one. Clear? So if it is linear, then it is to be supplied as a linear attribute. Okay. Now we have to return with what? The assigning of such parameter based on the input vector. Okay. That input vector what we have received. Okay. So once you receive the input vector, the same input vector would be encoded as per the ZZ feature map, and the ZZ feature map will return you the encoded vector. But you will not be able to see. You will be able to see only what? ZZ feature map. So let's have, you look at here. In ZZ feature map, what is the data vector we are passing? 0.1, 0.2, 0.3. Okay. So now in a 3-dimensional structure, so the 3-dimensional representation of the data people are now passing, okay, to the ZZ input. So now the ZZ input is now passing to the ZZ feature map encoding. Okay, this is the method. So the method will just receive this ZZ input as in that is a vector form of the data and draw it after receiving the output. Now you look. Now you look. Now you have no information, but you are only known that okay, this 0.1, 0.2, 0.3 are your data. How it was encoded, it is known by ZZ feature. It is taken care by the backend. Clear? Because this is one of the that is a representation facility provided by the Qiskit machine learning. Understood or not? Okay. Now, so let it be, if you are known already, so many codes are there, you may run by your own. Okay. My task was to only just demonstrate these all of them. So once I share, so you just go and run by your own. Right? So let's switch back to the circuit. Okay. यार सभी 1 minute. I need normal bottle. It's okay. So start with the variational quantum circuit or the quantum algorithms. Time now 3:05. 3:05. It's okay. Chalo. Now no hurry, try to understand. Okay. Now we have enough time till 4. Now variational quantum circuits are quantum algorithms. Okay, like variational quantum algorithms you say, or the circuit you say, these are the parameterized quantum circuits. We have to encode our data into the form of the parameters itself. Okay, and we have done these parametric encoding, means the parametric encoding is required here in a variational circuits. And okay, so because the data encoding mechanism we have already learned it. Okay, and the ZZ feature map technique is also supported by the Qiskit programming. So now if you see that based on certain rotational function gates, what gates? Rotational function gates, and with the random initialization we used to perform certain tasks like then that is approximation or the optimization or some classification, regression. These are tasks. Okay, so these tasks will be supplied based on some rotational function gates. Okay, so we have applied the rotational function gates. That is why the ZZ feature map is what? A popular one, because this is an implicit behavior of that feature map that allow us to encode our data into the rotational operators. Okay, and we need not to take care. We need not to take care how the data is getting encoded. It is to be taken care by the Qiskit framework. Clear or not? Now, an approach here that is using the variational quantum circuit, or to call it as a variational quantum algorithm. Now the PQC is utilizing a quantum computer to just full on that is taking the strength of of running your quantum machine learning task onto the limited capability of the quantum machines. Okay, so that in a minimal amount of a qubit space, at least you try to encode your data and you to see for the operational perspectives. Okay, now the PQC can be interpreted as the machine learning model. Okay, like parameterized quantum circuit itself. I told that whatever the machine learning models we have in a classical domain, we can transform the similar models into the quantum version, but we have additional models also which are specific to the data processing required by the quantum machine. Okay, So based on that one, this PQC is basically a machine learning model that deals in a quantum domain, okay, like a parameterized quantum circuit, or you may call it as, if suppose it is becoming like a classifier, so you may call it as a variational quantum classifier. These all are the topics, would be a lengthy one, okay. Now if you see the first circuit, that is in the next slide we have few of the examples related to the classifier. Here two instances are there, that is the data inputs are fixed, okay, that is the first thing. The gate parameters what we are passing over the circuit, that is with the data inputs which are remaining fixed, and with the free or trainable parameters, okay, means we can be able to train our parameters based on certain objective functions. We pass the data, okay, we check whether the training is done as per our expectation or not, we will evaluate, okay. Once the data is as per our expectation, so we will accept, otherwise we will retrain the machine, okay. So and this will keep continuing until your parameters have not been updated till as per your expectation, okay. So now this is the fixed circuit, there is no option. These are the rotational gates, variational quantifiers, some unitary transformations are applied. After that one we have measured directly. So once you measure, you are just looking at your optimizer results, whatever the result, but the input pattern is fixed. But here in these two diagrams, these are similar, means the interpretation of the diagrams would be similar, but the representations are different, clear. Here if you see only the quantum circuit, it is working with the unitary based on certain angles theta, okay. We are always measuring our information first and checking with the output whether our parameters have been trained accordingly or not. If no such there, so we have to just look at with the objective function and we have to update, okay. We have to update what? Our unitary transformation and again retrain the parameters, yes or no. And we will keep continuing with this fact till we are not getting our solution as per our expectation. Getting my point? So now these are other requisites, other essentials which are required for the quantum machine learning purpose. Not only we used to call like data encoding, feature mapping, or like GG feature map we people have done, okay. The other essential requirements are there. Everybody needs the quantum memory model to be processed, yes or no. The quantum model we need. If suppose if we have the enough capable quantum memory that can memorize the quantum encoded data points for the longer coherence of time, then our 99% problem related to the quantum processing would be solved. But we do not have what? A quantum memory till date, okay. Means the memory the people have proposed, this is one of the model I proposed, and this is the basic model I am just representing. The complex model I have already designed. I told you also I am working for the physical realization of a quantum memory with the ISRO for a satellite communication purpose. It's a photonic memory what I am going to develop, okay. But it's okay, let it be. There is no such interest for that one, but the thing is that the quantum memory, that the data encoded into the quantum state format, okay. We are looking for the data that is to be encoded in a quantum state format and to be retrieved in order to be processed by a quantum machine. Means whenever, like a classical processing model, everything initially comes into the RAM, yes or no. And once you have that is loaded your program means the instruction along with the data, okay. Once you have loaded your program into the RAM, it becomes process, yes or no. And why do we call it as a process? Because the automatic execution of such a process is allowed. The CPU is allowed to just fetch your instructions from the memory, okay, decode it, okay. After that one, try to execute your instruction based on certain demands. If suppose any required data is there, so then again the corresponding effective address of the data would be generated. It would be again transformed to the memory address register that would start pointing towards a dedicated address. The data would be fetched, stored in that is general purpose registers, okay. The processing will be done, again the data would be stored back to the memory. That is the cycle, understood. So in a similar way we cannot be able to proceed with the quantum machine because we do not have the privilege right now, understood or not, because our entire model is now struggling with the development of the quantum memory that is enough compatible to process with the quantum processor. You try to understand, the processor is very fast. That is the problem throughout the computer science. Why we are dealing with the different types of memory. Yes, hard disk, RAM, cache, yes or no? Yes or no? So we are looking for, why? Because to maintain the compatibility with the machines. Yes, because machine processing is very fast, but the memory components are slow in nature. So how do we make such a compatibility between them so that the speed mismatch would not be there at all? But here in an expectation of our that is a quantum machine, the machine is really exceptionally fast. We cannot like if you provide it a RAM, so the entire RAM can be just accessed in a moment of time. So what is now available to work on? Nothing. But in order to just get our information from the that is from the RAM itself, still we have to spend a log of n time. Now why log of n time is required? Look at the board. Look at the board. This is the simple architecture. This quantum memory can be designed using what? Using some qubits. These are to be called as qubits. So these qubits always remain in a 3 states, like left state, right state and wait state. Wait, you may call it as a superposition of left right. Okay, these are showing the directions. Okay, these are some quantum transistors. Okay, that would allow you to reach to the leaf nodes, where leaf nodes must be the dedicated address. Okay, like 000 to 111, we have very small 8 cells of memory. Okay, and at each memory we can be able to enough store one of the data character. These data characters belongs to suppose DNA patterns, ACTG character I used here. Okay, whatever the number of bits required, like 1 byte, 2 byte, 4 byte, it is depending on the that is word size that is to be contained within the quantum RAM. Now here, all such qubits remains active at a time. This is the superposition. Okay, these all remains active at a time. But what we people are looking for, like 0, 1, 0. So in order to retrieve this information of 0, 1, 0, irrespective of these all transistors, quantum transistors remains active at a time, we have to fetch our information to trace this address step and to fetch the data again in a backtrace. Clear? What is the height of this tree? If you can look, it's a login. It's a full binary tree over the 3 nodes. Yes, over the 8 nodes. It's looking like a binary tree or not? Huh? That's a full binary tree. And the height of the full binary tree is log n. Yes or no? So at least a log n time asymptotically is required in order to fulfill or in order to get the data from the quantum memory itself. Understood this fact? Okay. Now, so the RAM is required for the processing purpose of the machine learning. Now this is the swap test. Swap test is the another essential thing. Okay, that is required. What I told, that is the swap test. We have to just check for the similarity. Okay, for that one we have to perform the swap testing here. Now, this is a dedicated routine, that is to check for the quantum overlap of the 2 states. We have to check whether the quantum overlapping is there or not. Means the states are likely state or the states are dissimilar state. Like in an example of an inner product we discussed before half an hour. Yes or no? What was the discussion? 0, 0. Output is 0. 1, 1. Output is 1, 1. Output is 1. Yes. For 0, 1, 1, 0, output is different because of orthogonal states. So we have to check for the similarity, whether the 2 quantum states are overlapping each other or not. If they are overlapping, means their corresponding amplitudes can be enhanced. Yes or no? Now look at here. So the overlap is a measure of the similarity between the quantum states. This is an important line to just discuss here. Okay. So here the overlap is the measure of the similarity between the quantum states, and it will be used here in the calculation of the distance. That is a distance calculation subroutines. Like if you are just working for any classification of a data point, like you are inserting like in a KNN algorithm. You are inserting a data point, just looking for whether it is to be classified in which one, okay. Or like for a clustering algorithm, okay, we have to check it whether they are practically separated apart or not, okay. That is in order to cluster them accordingly as per their classification scheme, okay. Now, so how this swap test be performed? Here the 3 qubits would be taken. I told everything is intentional what I discussed since yesterday. This part we have done or not? Huh? And you know the other circuit also, that how do we implement the swap gate using the C0 gates, yes or no? Okay, you know the 3 C0 gates are enough capable, and one thing I am letting you know, if you look for this energy efficiency, that is the energy consumption of this operator, the C0 gates are slightly very simple one to implement, okay. This is the complex to implement within the quantum memory, that is within the quantum hardware, we should call like this, okay. Now, how it is working? There would be a 0, that is one state, 1 qubit initialized to 0. The other 2 states can be initialized to A, B, whatever you want, you may initialize. Apply Hadamard, and this is what? Controlled swap gate. After that one again Hadamard. First qubit will be measured, okay. First qubit would be measured. There is no impact on the first qubit, but based on certain controls, we people are allowing to check for the similarity between the data points, if they are similar or they are not similar. So how do we process? Look at here, we have certain mathematical expansion, like for all the other algorithms we have discussed till now. So still we have some mathematical expansion. Can you go for the mathematical expansions? Yes. Applying Hadamard, followed by controlled swap, followed by Hadamard. Simple. So once you go for the mathematical expansion of this one, the probability what you may be expecting, it would be around half. Okay. So if you get the half as one of the possible probability, it means what? That A and B are orthogonal, means 0 is included. Anyways, if any possibility of 0, means the states are not similar states. Understood or not? Because 0.5, it is equally likely to what? That is 0. Okay. So once you just look at the 0, means you will get to know, okay, these points are not similar points. So what to go for? Go for what? The probability, that is to observed as 1. Okay. So if you are getting your resultants with some probability of 1, it means what? Your states are identical states. Okay, that is to ensure about your similarity. Now this is the required mathematics. Okay, try to understand just in 2 to 3 minutes of time. Okay. Now look at it. It's simple. If you have understood, just please signal me your status now, whether you have understood with the mathematical aspects of the Grovers. If yes, just please raise your hands. Those who have understood, at least this is the signal for me. Okay, now second, what about the phase estimation? 2 main approaches I covered. Okay, so if you are comfortable, feeling yourself comfortable understanding these 2 approaches, then there is nothing in that one. You just look at here. Here, this is psi 0 state. Yes, look at here. This is psi 0. What? 0 AB. Yes. So I have taken 0 AB. Followed by what? Apply Hadamard. I and I, on which? I and I on the second A and B register, and Hadamard is fixed. Means this should always remain a 1. That is 1 qubit. A and B can be the different qubit wires may be taken in order to represent your states. That is in order to represent your data. Yes or no? For your data representation, this may be of n qubit size. So if you have n qubits of A, n qubits of B, so their similarity can be checked. Yes or no? Now, so when we apply this psi 1 here, the 1 by root 2, yes, 1 by root 2 of, if you apply the Hadamard on 0, it would become what? 0 plus 1 by root 2. So this is 1 by root 2, this is 0, this is plus 1, and the separated states are available with A comma B. Usually we need not to open commas. because there is no such separations available in a quantum state. We have now understood about the encoding. This is the basis encoding of our data. Whatever the quantum states you have, classical data you have, the same be represented here in a quantum encodable format. Yes or no? So now look at here, that is 0 AB, 1 AB. Now after that one apply the swap. Yes, the swap is what? It is a controlled swap. Not only swap, controlled swap. So whenever your data remains in one state, the information AB would be swapped as BA. That's it. Yes or no? Next is what? Apply Hadamard on the first one again. So once you apply the Hadamard on the first one, so the 1 by root 2, 1 by root 2 would become what? 1 by 2. Clear? So now after that one, this is what? 0. Okay? This is 0. And followed by what? AB plus BA. Followed by what? This is 1 by 2 of 1 of AB minus of BA. Now, once you go for measuring your answer, that is to measure the control qubit, the probability of measuring the state in a state 0 will be given by what? That is half of 0, 0, 0, 0 of this value. Okay, this is half of 0, 1 of this value. If you just think, this inner product is what? 0, 1. The inner product of this 0, 1 should be what? Orthogonal. Means it would become what? 0. 0 and 1 are orthogonal. Means the inner product value should be 0. So once you just look at 0, so this entire term would become 0. Yes or no? And this is as per based on the a plus b whole square if you just expand. Okay. So just after the expansion, if you see here, this is BB, AA, this is suppose AA, BB. Okay. So these AA, BB are still the similar states like 0, 0. So for 0, 0 you will have what? 1. So these all terms will become 1. Okay, and this would be a twice of these states. Okay, so once you take the common with the value of 1 by 4, you will get half plus half of a plus b of whole square. Understood? This is a modulus square of a and b. Means whenever we want to just get the information related to the similarity of the different data points, so that half is already included. Getting or not? Half is already included. I am only checking for the remaining half. Okay, whether the remaining half is available or not. If yes, then the corresponding state would be identified. Otherwise, we will declare not similar. Clear or not? Simple mathematics, it was there. Now, you come on to the possible thing. What's the time, madam, please? 3:30? Huh? 25. So now, I am on time. It's okay. So are you all comfortable? Comfortable, then no problem. Now look, that is the thing, that is the machine learning algorithmic selection. So for machine learning algorithmic selection means you know the tasking methods, whether you are applying the classification, clustering, regression, whatever, the prediction purpose, for whatever the purpose you people are applying your machine learning solution. The same we need to encode. The same we have to transform in a quantum machine format. So how do we transform? For transforming that one, if you connect it with this, if you connect it with this ladder, yes or no? Now everything is connected here. You look. If you just memorize the ladder, so now once we are known that what machine learning algorithmic selection we are having in a classical viewpoint, now go for choosing the design strategy first. Okay, because the data can be encoded. We know that how the data can be represented over the quantum circuit, but how do we how do we code our quantum algorithm equivalent to the machine learning algorithm? Yes or no? Otherwise you have your own separate quantum algorithm, because now this point onward you may just visualize, okay, the quantum may be one of the possible superset. Why? Because possible superset, it has not been declared for all. I told you yesterday, the supremacy has not been concluded at all. Okay, what I am letting you know, the simple thing is that the task which are being done by the quantum machine, that cannot be done by the classical machine. Yes or no? Means few of the tasks which are separated only for the quantum machines. The quantum machines are capable of just doing like a variational quantum circuits. Yes or no? So this is the dedicated circuit to become as a classifier, and if the classifier is available for us to classify certain data points, okay, based on our that is output targets, okay, input labels, output targets. So based on that one, if we have a specific classifier in a quantum machine learning, so the same classifier may not be available here in the classical one, okay, because the processing of the data, that is based on the database processing, the working of the model would be different, okay. Now, so how to go for? Again, to choose the classical, that is a quantum design strategy for realizing these all algorithmic selection. And you know, because two of the basic algorithmic selection we people have already done, that is an amplitude amplification. What's the objective of amplitude amplification? Learn it in the morning session. What's the objective? What is the objective? That is to amplify. Amplify what? The desired states. Yes or no? To amplify the desired states. Means whatever, suppose like you are doing for classification. So whatever the classified data is there, okay, we have to amplify their own what? That is amplitudes associated to the states. So now this is a dedicated procedure. I told you that is Grover's. Grover's is an algorithm. This is a special case of what? Amplitude amplification. Okay, so amplitude amplification is a generic task, like dynamic programming. Dynamic programming is a generic task. Okay, that is the way to solve our solutions. Okay, the way to solve our problems. Okay, but we have the several number of solutions, like we have the Boolean knapsack to be solved in a different way. We have the, that is, traveling salesman person problem to be solved in a different way. Yes or no? So the ways of identifying, analyzing as well as the solving approaches, they all are different. Clear my point? So now, so this is a simple approach of not to be called as a simple approach because it's a complex algorithm to understand. Grover's is simple to understand. Amplitude amplification, if you look forward, so it's really complex to understand. Look at here. This is what we people are applying. These are some operators. Okay, these are some unitaries which are to be applied for some k number of times, and this k number of times to be supplied, like pi by 4 of root n. Yes or no? So pi by 4 of root n, so we have to supply the same task means phase inversion followed by amplitude amplification. Okay, we have to just iterate on. But if you see the operational specification here, this is the same. Yes or no? Are we did in for that is marking an amplitude or not? That is to negate the amplitude. For negating the amplitude, I minus of twice of psi I. Yes or no? That is the solution states, what we are looking for. And what about that? This is what? 2 psi psi minus of I. So where this psi is a superposition state and this is a marked state. Clear or not? So based on, because of the approach is generic, the understanding over that problem, that is how it tackles the problem in a quantum domain, it would remain same. Okay. Now proceed. This is another strategy we have already discussed, phase estimation. Yes or no? And based on the phase estimation, this is the required algorithm. This is equivalent to this circuit only. So based on this circuit, if you see, apply the Hadamard on all the control registers. Yes, followed by what? For each control qubit, like j should belongs to 0 to n minus 1. What to apply? If j is equal to 1, then the control unitary transformation 2 raised to the power j to be supplied always in order to identify the value of e raised to the power 2 pi I 2 raised to the power j of theta, because your information gets encoded in the form of 2 raised to the power n into theta. Understood or not? So after that one, we have to supply what? The QFT inverse, and once the QFT inverse you apply, you will get the corresponding solutions. Understood or not? Are clear or not? So these are not only, I told, like if you are going for your phase estimation perspective also, that is Fourier transform, inverse Fourier transform, these are the complex mathematical things that is to be understood first. I told This is only what may be your perception or what may be the visualization you have in your mind, it would be still very small thing. It's a very highly complex system, it's a dimensional system, and each dimension is exploring the same number of states. Means what is happening in a one system, the same system is also ready with doing with the other aspects. Clear or not? And out of all the possible expansion of the system, we are just checking particular system among which we are just extracting our quantum states which are desired to us. Okay, so try to understand these all things. Now come up with the approach of dimensionality reduction. There is nothing to just discuss with that. We just try to understand what is remaining to understand with the dimensionality. I told you, for designing the dimensionality reduction like using a QPCA, quantum principal component analysis. So for that purpose, only I need to compute the covariance matrix in an efficient manner. If I would be able to compute the covariance matrix in an efficient manner, so I would be happy at all. Yes or no? So because the covariance matrix takes the time of n cube, that is as worst case. But if the same task can be solved here in log of n time, so I would be happy, okay, at all. Okay, so now how to apply? For the principal component analysis, the problem is what? The problem is the curse of dimensionality problem. Okay, the problem is curse of dimensionality, where the dimensions of the feature space scales exponentially. It is scaling exponentially, okay, for every data set. So now because of that one, the dimensionality reduction we require. Okay, we are just reducing the dimensions. Okay, now it decreases the data set dimension, storage space, as well as the time to prepare a machine learning model. So because of these all facts, this was one of the objective of the quantum machine learning. We people are looking for enhanced feature extraction techniques. Yes or no? So the quantum based principal component analysis would give you to get the extraction of your data in a efficient manner. Okay. Now the dimensional reduction is here to transform the high dimensional data into the lower dimensions. Now the task is different. Okay, higher dimensional data representation is available to us, and we are here to just reduce the dimensionality of the data set. And based on what? The ranking of the variance. Wherever the maximum variance is there, we used to extract what? The principal components. Okay, the significant register. Clear? Because the target register we are not interested in. Okay. So now this is how HHL algorithm, this is one of the famous algorithm that is used to solve the linear regression problem. Okay. I just told you na in the previous, this is one of the specific that is method to be used. Here you must see linear, okay, for linear regression as well as for support vectors also you may use. Okay. There can be different possible designs. If you know the quantum design, how you are applying for just developing another or the optimized quantum algorithm, that would be up to you. Clear my point? So let's proceed with this to the next. So this is a simple, that is a classical, this is one of the famous paper. This is quantum algorithm for beginners. It is one of really a good paper. If you be able to, that is, you just directly you write down quantum algorithms for beginners. Okay, you download that paper and just read it. It's worth reading paper. Time over. I'm just about to complete, madam. Just it would take. So just look at here. The classical processing what we are requiring. What's the time, ma'am, please? 50. 50. Okay. 10 minutes left. Just wait. Now data we are just encoding. Okay. Now this is the transformation followed by this is the preparation of a superposition, and then we are applying what are unitary transformation. So once you are ready with your state preparation followed by a purity calculation, this is the swap test. Why the swap tests are required? You know now. That is to check with the similarity between the quantum states. Okay. So now based on the similarity we used to go for the classical post-processing system. Okay, we have to check. Not only the single that is a simple approach is to be applied, here is the complex approach using the same PCA mechanism to be applied. Okay. Now demonstration of the dimensionality reduction is possible, but if the time is okay, so then you allow to let me know, otherwise I would be going to share you that the code, that is the piece of code, and if you understand, so you directly, because if the algorithmic understanding is there, okay, that how the quantum PC algorithm is actually working, okay, so the simple demonstration you can also be able to just realize on your machine. Your machine is ready, okay, just copy the code, run the code, okay, by running the code you will get to know. Otherwise, if your machine is still not ready, so you have the option to just set up onto the Google Colab, run the same code, the code will run. Okay, so you will have the option to just go for running it. Now this is a simple, that is another, that is machine learning algorithmic analysis. So as per the analysis, like this is the progress, like quantum support vectors, k-means clustering, dimensionality reduction, and this neural network. These all the people are doing. Okay, but based on that one, I am just letting you know that what kind of speed ups are achieved and what kind of algorithms we people are doing. Means the people are using which kind of quantum algorithms in order to achieve the speed ups. Like if you see here, the quantum support vectors. Okay, so support vector machines, based on the Grover mechanism, it is achieving the quadratic polynomial speed up. Okay, so if you understand the Grovers, that was only my objective. If you understand the quantum fundamentals, quantum routines, quantum algorithmic aspects, so you will be able to transform from your classical machine learning knowledge into the quantum machine learning knowledge, nothing else. Clear my point or not? Okay, if you see the k-means clustering here, so here in the k-means, it's an optional whether you use the Grovers or not. Okay, because for clustering purpose you may just go for applying the swap test, distance calculation, these all things. Okay, so based on that one also you will just work for the clustering algorithms. Similarly for dimensionality reduction, we know that is for dimensionality reduction like this PCA, that is to identify the principal components, there is no use of Grovers, because we know the other quantum subroutine which is significant for the design of the QPCA is phase estimation. So because this analysis was available based on the Grover, okay, but I am letting you know these are the two specific design strategy. If you know in a full, or you have fully understood the design strategies, you would be okay and you proceed for the quantum machine learning based solutions. Understood? There would be a simple model demonstration. If you say so, I will share it with you. If you understand the basic, that is like support vectors also. So I will share you the code. You just run it by your machine and just analyze, because nothing is there. Data set is there, transformation is there, and we have to visualize, because once we run the model on the data set, it takes the time. First it would load the data set and it process slowly. We do not have in-hand workstation with us. Okay, this is a simple laptop. So over which processing of the real data set would be again a time consuming one. Clear my point? So this is all about. As the concluding remarks, just to be taken only, that the machine learning begins with the encoding of a data, analyzing based on the data, that is the choosing of your the data encoding methods, feature encoding, feature mapping things like for machine learning, ZZ feature map we people have already done. Algorithmic design strategies are still a must for going towards any quantum machine learning based solutions. And the dimensionality reduction significance, we can get to know that for the tasks which are required to be solved in order of n cubic polynomial time, the same task can be performed here in a logarithmic value of n. So this would really be a great task if you just go forward for the dimensionality reduction purpose using our a quantum based approaches. Clear? So now that's all about. These are the certain references related to this. These are some the good books like Peter Wittig. You must be known. Okay, this is the good book to learn. This is one of the fundamental book, Frank Zicard. Okay, if you just go for this hands-on quantum machine learning with Python codes. Okay, like Python means no, there is a Qiskit codes. Okay, they used to write down like is Python, because the people know Python. Okay, the people know Python. So like the courses the people used to run, if I run the course like quantum computing, so nobody will have the interest. If I run the course like quantum machine intelligence, so everybody will show the interest. Yes or no? Because looking for the artificial intelligence, everybody is now transforming towards what? AI. Everybody is doing AI. Clear my point or not? So like these are the things to be discussed. That's all. Okay, so from my side, almost, madam, I maintained my commitment. Sorry, thank you very much. And 5 minutes early. But within 5 minutes, I could have been able to demonstrate the thing. But it's okay. You just get the codes. Okay, I'll share with the madam. Okay, but in late evening. Right now, I would not be having time also, because I'll have to check out. Okay, and have to that is connect with my flight. So just try to understand. Late night you people will receive. Okay, it's okay. So I tried at least to make you all comfortable, but anyways, now madam, valedictory session, everything over. Now means participants happy. Yes or no? I do appreciate if because the faculty participants are seated in a room and they are actively listening, attentively learning the things, means it's really an appreciable thing. I can't attend. अभी इसको बंद कर दे तुम्हारा साउंड सिस्टम.
Good afternoon all. We are at the edge of our learning marathon, the FDP on Foundations of Quantum Machine Learning. I invite the dignitaries, Vice Chancellor Sir, Pro VC Academics Ma'am, Convener, Co-Convener, and our today's resource person to this valedictory event. Now I would like to request our Co-Convener, Dr. RVS Lalita Ma'am, to present the report on this FDP.
Honorable VC Sir, Dr. MB Srinivas Sir, and Pro VC Madam, Dr. S. Ramasri Madam, and our resource person, very eminent person, expert in knowledge and everything, technical person, more practical person, Sri Dr. Kapil Kumar Soni Sir from NIT Raipur. So a grand and all the participants, a grand welcome to the valedictory function. Now I am going to give a brief report on what are all we learned in this workshop and what we have learned from this workshop. In the first day, Dr. TSL Radhika Madam from BITS Hyderabad, she gave a clear insights about the basics of quantum computing principles and mathematical knowledge about it, and she explained us how to use IBM Composer for evaluating gates and fundamentals. And also she told us how to evaluate the quantum circuits in a simplest way. And next, coming to second day, Dr. P.V. Subbareddy Garu from NIT Warangal, he gave clear mathematical knowledge and working principles of quantum gates, and he clarified all the doubts about the quantum computing evaluation of the gates. And very good explanation sir has given, and he has given a clear insights about the quantum computational units. And he also explained the Deutsch algorithm, and he gave some introduction to the other algorithms also. And next, third day, coming to Professor Dr. E.S.N. Raju sir from NIT Warangal, he gave clear insights on this quantum image processing. And he is also a very practical oriented man. Sir gave two examples, how to convert black pixels into white pixels, how to construct a quantum circuit, how to design a quantum circuit and all, how to implement the algorithm as a part of the quantum circuit, and how to work within the IBM quantum composer. So sir also given some programs, and he asked us, he conducted a hands-on session on that. So we have very much learned in that particular topics and domain. And fourth day, coming to our Dr. Kapil Kumar Soni sir from NIT Raipur, he gave, I don't know what to say, he dwelled into the quantum computing principles, and he gave clear insights of the introduction to quantum programming. We learned a lot how to implement quantum circuits in Python. And he told IBM Composer in very depth several programs he have given, and he explained us the programming knowledge as well as the execution, and also he explained about AER simulator, and also he explained how to configure IBM Composer when it is really executed on the quantum computer. So thanks a lot sir. Quantum computer is our dream. You make us learn how to execute that particular program on the real world. And next, today's session, he explained about the dimensionality reduction problems and the data encoding methods, and what we expected is quantum machine learning. He explained all the topics in the quantum machine learnings, in all the subdomains of the quantum machine, how to interconnect machine learning principles and deep learning principles with the quantum computing. So thank you very much sir. We are very much grateful for having your sessions, and we have got some idea in quantum computing. Sometimes we could not answer your questions because of the short span, but we'll prepare and we'll follow your fundamentals. And as per our VCSL session, as a part of the quantum computing workshop, sir asked us what is the outcome we are going to get. So this workshop is merely meant for working on the quantum computing. So we planned in this way, with the help of the Sudharani madam, we asked participants to work on papers, research papers, not necessarily the complete one, at least they have to initiate the papers. So in this, First one, introduction, related work, methodology, and mathematical model, and classical models, quantum models, comparison. We have given some sections and we asked them to submit. So in that, we wonder that Dr. D.V. Prasad sir, he completely given the complete research paper which was reviewed by our Kapil Kumar Soni sir. Sir reviewed that paper and he gave some suggestions also. And next, coming to Sujana madam, she also executed all classical models and quantum models, and that paper is also reviewed by sir, and sir gave some suggestions. She will definitely work on that, sir. And next, coming to Neeraj sir, he gave his plan about your research in the view of quantum computing. So that is also appreciated. That paper also was viewed by sir. And next, coming to PNS Lakshmi madam. So she also has given some work and method plan according to her view in quantum. I appreciate in all papers that they all included quantum computing algorithms in their research paper. So that is what we require. So thank you all for your participation and working with the quantum research, quantum computing research. So thank you very much. And some of the students, some of the participants or faculty members have answered well the queries posed by the resource persons. So for them also we are going to give appreciation certificates. So in that Vijayasri madam is there, Sridevi madam is there, and Durga Devi madam, Y. Srinivas sir, and Dr. A. Arun Kumar sir. So this is the work what we have done so far, sir, as per your instructions. And we are very happy to have sessions with all these resource persons, and they also planned the sessions according to the sequence, first, second, third, like that. They discussed with themselves and planned these sessions. Thank you, sir. Thank you, one and all. And I give a great gratitude and thanks to our Srinivas sir and Ramasri madam and our Pro Vice Chancellor, Dr. A. Ramesh sir, for giving permission to conduct this sort of workshop. Thank you, sir. Thank you.
Thank you, ma'am. Now it's time for certificate distribution. I request the dignitaries to hand over the certificates to the best participants as mentioned by our co-convener, ma'am. The first person is Dr. K. Venkateswar Rao from Aditya University. I request all the dignitaries to please join for the certificate distribution. Sir, please, sir. Next, Mrs. C.H. Sujana. Next, Mrs. C.H. Sujana from ESET. Next, Dr. D.V.S.S.V. Prasad sir from Aditya University. Next, Mr. Neeraj sir from AUS. And the next participant is Mrs. PNS Lakshmi ma'am, ESET. The next participant is Dr. B. Vijayasri ma'am, AUS. I think the event is very drowsy, you can encourage them. The next participant is Mrs. BMS Durga Devi from ESET. And the next participant is Mr. Y. Srinivas Rao from ESET. and Dr. G. Arun Kumar from AUS. Thank you, sir. Now we came to a special moment for felicitating our today's resource person, Dr. Kapil Kumar Soni, sir. Now I request all the dignitaries to come forward to felicitate our today's resource person, Vice Chancellor, sir, Ramashri ma'am, Convener Sudharani ma'am, Co-Convener Ravita ma'am. Good round of applause. Thank you so much, sir, for accepting a small token of our gratitude. Now I request our today's resource person to speak few words about this event.
Actually, by looking at the tired participants now, I would not consume more time, because I am fond of that is talking as well as what do you say like speaking at all. But I tried my all level best to make you all comfortable. There should be certain vision in the teacher's mind. Okay, so my vision was only very simple, that to make you all comfortable in that is fundamentals related to the quantum machine learning or to be in the core of the quantum computing. Okay, so I tried my all level best in all of these aspects, but it is still like in a similar manner what we used to communicate to the students, but how much the people are grasping and how the people are proceeding towards, okay, that would be up to you. Okay, so if you have certain growths in quantum computing in a future perspective, so for all of you, my best wishes will always be available, and in any case, if you need my help, so you just please contact me also. Okay, thank you very much. And sorry, I forgot just to give the thank to the Vice Chancellor sir, Srinivas sir, Pro VC ma'am, Rama madam, especially that Lalita madam and Sudharani madam. This is a hard task to just remember name, but I know the names. Okay, so I am really thankful for you all to invite me for giving these expert sessions in your FDP, and for all, especially for the participants, because you people have attended very that is active manner, in very active manner you people have participated in the classroom, because it's a mutual coordination among a teacher and a student. Okay, if I look a very boring faces or the sleeping faces, so I cannot maintain my own energy level. Okay, but I am really thankful to you all people were having the smiling face, attentive face, so it gave me a lot of energy in order to just deliver my lectures. Okay, so thank you very much to all of you. Okay. Good.
Thank you so much, sir. Now I request Mrs. Sujana ma'am to propose the vote of thanks.
Thank you, sir. Good afternoon to everyone present here. I am Sujana, Assistant Professor, Department of Computer Science and Engineering, Aditya College of Engineering and Technology. It's both an honor and a pleasure to deliver the valedictory address for this enriching faculty development program hosted by Department of CSE, Aditya University. Over the past 5 days, we had the privilege of engaging in insightful discussions, hands-on sessions, and collaborative learning, all centered around the theme on foundations of quantum machine learning. The sessions led by the esteemed resource persons have certainly expanded our perspectives and deepened the knowledge of quantum. This FDP has not only helped in upgrading our technical skills and pedagogical knowledge, but also fostered a spirit of innovation and interdisciplinary learning. It has reminded that as educators, we must continuously evolve, not just to stay relevant in ever-changing academic landscape. I take this moment to thank the organizing committee for their tireless efforts in curating a well-structured and impactful program. A heartfelt thanks to our Aditya University management, leadership teams, deans, associate deans, HODs of Aditya University and Aditya College of Engineering and Technology. With equal pleasure, I acknowledge the members who have accompanied our resource persons. To all the participants, thank you for your enthusiastic involvement. Your active engagement, thoughtful questions, and collaborative spirit have true highlights of this FDP. Wishing you all the continued success and growth. Thank you.
Thank you, ma'am. Now I request everyone to rise for national anthem. Yes. Now I request someone from the participants to give a feedback on this 5 days FDP. So please.
Good evening, dignitaries and my dear participants, friends and colleagues. I'm sorry, it's 4:20, I know, I don't want to take much of your time. Okay, sir. Sure, sir. It just nothing is there, just I would like to put it in quantum terminology. Basically, day 1 to day 5 already Lalita madam explained all the sessions. We have attended all the sessions in a series. And right from day 1 to day 4, actually whatever my perspective, what I experienced basically, each and every session was incomplete, I felt. But day 5, today, all these qubits are connected, correlated, entanglement. Sorry, sir, if anything wrong. Soni, sir. Yes, sir. Connected, correlated, totally entangled, and finally, fully executable, fully functional quantum circuit was made today, totally. And that was done by Dr. Soni, sir. It's really, in a really a beautiful way, because of his execution of codes, and I request you to provide those codes, sir, and which will be useful further. Basically, actually earlier, QuizKit environment, most of us, I don't know, about me, I couldn't understand properly, because it's IBM, it's really hard to understand basically, but whereas once your codes are there, totally that visualization is there. What is the Hadamard gate, what is the control, what is this XOR gate, NAND gate, NOR gate, everything was visible through code. That's really good actually. So that's what I said, that's why I felt today that all these qubits were connected, correlated, entangled, and fully functional executable quantum circuit was made by you today in a beautiful way. Thank you, sir. Thank you so much. And I appreciate especially Lalita madam for her pains in conducting this FDP totally. And finally, all the faculty members of Computer Science Department for their idea in conducting FDP in this particular emerging area. Really, thank you, sir. Thank you so much, because I am from out of domain. I am from mechanical engineering. I started recently for the past 1 month studying all the things, qubit, this, that. A lot of things are there, all the terminology. I was getting confused totally, but I could not. But today, I am feeling that yes, I can work. If not today, tomorrow I will get it, totally. Thank you, sir. Thank you so much.
Thank you, sir. Any other participants would like to share their feedback? Yes, sir has already promised bus will wait for us.
Respected dignitaries, first of all, good evening all, and myself, Dr. Vijay Sri, one of the participants of this QML program. And first I would like to thank our Kapil Kumar Soni sir. He has interacted with us for 2 days with his proficient expertise, and he has given, he is very enthusiastic than the participants. He want to deliver whatever the content he want to deliver to us without any hesitation. So I am very impressed with that kind of behavior, sir. Thank you so much for being with us these 2 days. And as Professor has said that these first 3 days we have the basic knowledge, but we don't know how to apply, where to apply, how to connect all these and all. And with today's session only we have a complete idea how to connect and how to implement for a real-time problem, if it is from writing algorithm to the designing of the circuit and correlating the qubit information to the classical bits also. Thank you, sir. Thank you so much.
Thank you, ma'am. Anyone else from the participants? Yeah, now it's time for national anthem. Everyone. Yes, yes, please.
So, thank you very much. Good evening to all. He forgot that I was also the participant last 3-4 days. Okay, it's really amazing because we had some excellent speakers coming for this quantum machine learning workshop, and in my 30+ years of teaching research experience, I never came across somebody who spoke with so much passion. Amazing. Like what Dr. Vijay Sri said, the kind of enthusiasm, he was more enthusiastic than the faculty themselves, so that's a kind of temperament, and then that urge to teach and train people in this new generation of technologies is something that's very amazing. So we are really so thankful to you for coming all the way and then spending 2 valuable days with us. Then I should also thank Dr. Lalita and then Dr. Sudharani for taking the initiative to organize this workshop. It's not so easy because they had several sittings trying to identify the right resource persons, talking to people, and then fixing up the titles. All those things were there, and which they really worked on and tried to come out with an excellent program. That really made everybody so happy, because I could see that fun and excitement in you while you were learning this very, very cutting-edge technology. So special thanks to Dr. Lalita because, because as somebody said, she was, running around and then trying to put everything together and to make sure that deadlines were met and everything happened in a very systematic and a truly intellectual environment. But what you don't know, what happened in the background with Dr. Sudharani. Sudharani being the HOD, she had to juggle between the HOD meetings, academic council meetings, while she was also attending to here, she had to do many things. A truly quantum parallel kind of activity that she was, so it's such a wonderful thing that both of you really took the initiative to organize this. And this lady, she was also working many things in the behind, in the taking care of the people and making sure that everything happened in a systematic and a timely way. Okay, so thanks so much to the organizers, and also thanks so much to the participants as well, because it's not easy to sit through 5 full days of the activity and listen to the lectures and also participate in the lab. And I could actually see the urge in you to learn these new technologies, and possibly with an intention to carry out research going forward, and possibly also do PhD where you have not done the PhD yet, okay? So these are all the real good things that came out of this workshop. I think after I came here about 10 months ago, this is the first really high intensity workshop and with full participation that I could actually see. So thanks so much for all your participation. So when it comes to teaching and education, we all talk about outcome-based education, right? So the research also has to be outcome-based, okay? So therefore, our hard work starts now. Now, we should not stop this year. We need to take it forward. As Dr. Lalita said, you know, some of you actually have written some papers, showed it to Dr. Kapil Kumar Soni, and then he also appreciated work. So what we now need to do is all of us should form a team, okay, and should carry this work forward. And as the first gentleman said, I don't remember his name, said we should, for next several years, we should all be entangled and then never collapse in the process and work as a team to do some very advanced work in quantum machine learning, okay, quantum computing as well as quantum machine learning. So I request Dr. Lalita and Dr. Sudharani to take the lead and make sure that we are all part of the team while we continue research in this area. And possibly next semester, if not the coming academic year, the next even semester, we can even offer quantum computing as an elective to the 3rd and 4th year student. So I want some of you to take the lead, okay? So let us form a team, but before that, I want to make sure that all of you agree for that. So can you raise your hands? How many of you would be really willing to be part of this effort and take the research in this domain forward? Can you raise your hands? Okay. So come. Ma bangi milani photo diskunta. Keep your hand raised. Okay, yeah, very good. All of you virtually raise your hand. Okay, pass on that photo to all of us. Okay, so we will identify you through the hand that you raised. Okay, so you know, he made it so simple. Even a dumb person like me, by sitting for a couple of hours, I could actually make out what is happening. I could understand at least, but now I need to go back and work myself to fully comprehend what is happening and invoke all those tools and then you know, make sure that I also work along with you. So what we do, we now formed a team, okay? I'll get the names from both of you, okay? So we will meet once in a week, every week. Please identify what time will be convenient for all of you. And let us identify a few problems, okay? And then let us form sub-teams and start working on those problems to see whether something comes out of our collaboration to publish papers, okay? So maybe as a first step, now that you have the complete list of people attending, maybe you can call for a meeting next week, okay? Whichever day is convenient, okay? Time, maybe for an hour we can meet. We will discuss about what are the areas that we would like to work on. So there is some quantum computing, there is a quantum image processing, in addition to what Dr. Kapil Kumar Soni taught us over the last couple of days. So all these things, depending on what you found more interesting and what you found fascinating, you can form teams and start working on those topics, okay? So one thing is that we will start carrying out research by forming teams. The second thing is, how many of you have seen the ANRF announcement, Anusanthan National Research Foundation? They have announced the call for proposals. Okay, have you seen? Because the mail was circulated, I think, on WhatsApp. Okay, so ANRF, as you know, last year many of you applied, so the same thing, okay? ANRF, that's Anusanthan National Research Foundation. Let us submit proposals, okay, project proposals, and let us identify some research topics and then submit project proposals. We'll all be together in that. And then I request Dr. Kapil Kumar Soni, if you could also be a co-investigator or a main investigator, either way. So if you are writing proposals by yourself, You may, depending on, based on your interaction so far, if you could identify a few people, we can help you to identify, could involve them as co-investigators, or we can write the proposal and request you to allow us to. I'm not looking for immediate answer, but depending on your comfort level, you can tell us, okay? So let us make sure that at least half a dozen research proposals will go from us for funding, okay? Even if one proposal gets funded, that would be a great achievement, and a salute to Dr. Kapil Kumar Soni for educating us on this, okay? So I know all your mind is on the buses, so the buses will not go till you are there, okay? Let us split now, but I request you, this is a great opportunity to work in this cutting edge area, and then Aricha University being a new university, if you work on those areas, the possibility of getting recognition is much faster. Papers get published, your citations will increase, your impact factors, all those come into picture, your H indices, I indices, all will go up, okay? So thanks so much for lifting your hands, because you're all agreeing that we should work together. So let us work together and let us pave the way for our progress in the area of quantum computing and quantum machine learning, okay? So all the best to you, please.
Thank you, sir. Thank you. Sincere apologies. I have observed that in spite of his busy schedule, our Vice Chancellor, sir, okay, he is coming and learning, listening to the lectures at least 2 hours a day. So thank you very much, sir. Yes, sir. Yes. After national. So let us raise for national anthem. Thank you. Let us gather here for a group photo. After group photo, we can wind up the session. Happy learning, happy weekend.